We at Math to Market asked ourselves, how does the mechanical strain in lithium-ion electrodes induced during charging and discharging affect the aging behavior of electrodes? To tackle this question, we induced, together with a group of Professor Vanessa Wood at the ETH in Zürich, the EU-funded project SOLVED. In this project, we address the mechanical degradation of lithium-ion electrodes during charging using an experimental as well as a theoretical and simulative approach. The experimental approach is to analyze the microstructure of an NMC cathode and a graphite anode through 3D in operando X-ray tomography and through electrochemical characterization. The digital approach is to use geodict to simulate the local stresses and expansion of the electrode microstructures due to the local lithium-ion concentration in the active material during charging and discharging of the battery. The simulation monitors and predicts the influence of microstructural changes on the battery performance. There are several reasons why a battery may age and finally fail. One important mechanism contributing to this aging is mechanical degradation. Lithium that enters an electrode during charging or operating a lithium-ion battery leads to expansion or contraction of the active material. The local lithium concentration determines the extent of this expansion or contraction that causes mechanical stresses on the micro and macro scale. These stresses during cycling of the battery lead to degradation of the material due to cracks, delamination, and deformation of the inactive layers and the casing. The altered microstructure is said to age, and it suffers from capacity loss and damaging effects like lithium plating. If a battery is cycled, of course, these degradations sum up during each cycle. To simulate the cycling, we start with a charging simulation using the BatteryDict module of GeoDict. This gives us the local lithium concentration at each point in the active material. The resulting local concentration field is now fed into the FieldMath solver in GeoDict to calculate the resulting local stresses and the expansion of the structure induced by the differences in the local lithium concentration. The deformed geometry is now given back to the battery layer solver in BatteryDict for further charging of the material. After that, we perform another expansion step and so forth. We repeat this until the battery cell is fully charged. Thanks to our cooperation with the group of Professor Wood at the ETH, we have the opportunity to validate our simulations with experimental data. The experimental data consists of two major parts. First, in operando X-ray tomography measurements of an NMC cathode and a graphite anode. The second part are electrochemical characterizations of the same materials. The combination of these measurements gives us the possibility to parameterize and validate the simulation. On the simulation side, several improvements had to be made into GeoDict to allow for this kind of complex simulations. To speed up the computation, the layer solver in GeoDict is adapted for battery charging simulations. Cycling protocols were defined to cycle the virtual battery to control the charging and discharging simulations for the automated coupling of electrochemical and mechanical deformation simulations. And the well-established GeoDict workflow of importing, processing and analyzing 3D image data of battery materials is expanded by using powerful structure generators to create realistic digital twins of the battery materials and a virtual battery. Additionally, the damage due to mechanical deformation is simulated. For the validation of the simulation results, a comparison with the experimental data was done. The simulated expansion of a cutout of the graphite anode is compared with the corresponding in operando measurements to validate the simulation. The total expansion of the particles is 10% in the measurement and 9.8% in the simulation, with free boundary conditions for the simulation. A comparison of a slice of the structure for 60% state of charge is shown on the left. Voxels with the same material in the measurement and the simulation are shown in white for electrolyte and in gray for graphite. Voxels that are labeled differently in the simulation and the measurement are shown in blue and red, respectively. These differences are caused mainly by the fact that the simulation results shown are for isotropic expansion. Due to the orientation of the graphite flakes, the real expansion is anisotropic. This is observed in the measurement. This anisotropic expansion of graphite will be simulated as a next step in the project. Reliable quantitative simulations are the way to a time-saving and streamlined approach to find new battery prototype materials with superior lifetime and performance. This unique digital workflow represents an efficient, state-of-the-art methodology to digital R&D material design for energy materials in e-mobility and energy storage. Thank you for your interest, and if you want to follow up on this topic, please feel free to contact me at Math to Market. Thank you.